Hi, very good evening, everyone. Thanks a lot for joining in for the day four session on traction motors and controllers. Uh, we will be starting the session in 6 more minutes to go. So if you have any questions from the yesterday's session, so please do share your questions on the chat box. Or if you have any learning expectations for the today's session, do share us the required learning inputs for you on the chat box so that I would be able to drive the session to meet those needs. So yeah, we should start back at 5 p.m. So until then, I'll be muted here. So yeah, please do interact if you have any questions in the meantime. Thank you. All right, so I think just 2 minutes to go. We're just waiting for everyone to join in. Should be starting exactly at 5 p.m. So if anybody would like to ask any questions, so we'd be quite happy to address them just before the session starts. Or if there's anything that you want to take away from the learning content of today, please do drop the message on your chat box that we can quickly discuss. So I believe everything is going on great until now in terms of the learning. I believe you're enjoying the sessions that has been going on for the last 3 days, and this is on day 4, which I'll be ending my part of the sessions. And tomorrow, Mr. Krishna will take over the session, and he will be addressing the session on uh, designing or selecting a motor and other components, but performing the calculations in an Excel sheet. So it will be a hands-on practical session tomorrow. So you would require to have a laptop and preferably Microsoft Excel. So because we will be using Microsoft Excel to draw the data, and it will be quite amazing and funful to learn for you. So yes, so please do have the laptops with you tomorrow. So it's just 5 right now, and we will just have it started. All right, so very good evening, everyone. Thanks a lot for joining in for the electric vehicle subsystems and technology course. Today is day 4. We will be covering up our discussions on traction motors and traction controllers. So I believe you have enjoyed the past sessions for the last 3 days. So let's just begin ahead with the very first topic on the traction motor as a requirement. So what exactly the difference between the traction motor for another application and a traction motor for an EV application, right? So if you take any application of motor for another requirements, let's say something as an industrial drives or any automation requirements or any other requirements, which is non-tractive requirements, right? So the motor is the load on the motor is quite static in nature. So because you have a predefined load parameter, and you just have to know what exactly the bandwidth does the motor operates in, and you can just optimize your motor design for those requirements. But when you take a motor for a traction requirements, right? So the motor operates very widely in various regions of operation. So if I just draw some lines here, so this is the motor operating motor torque operating regions across the drive cycle. Supposedly this was defined for any specific drive cycle, like WLTP or something like that. So the drive cycle has been defined for a duration of about 1,300 seconds. So when if you consider this is in a realistic condition that we should drive the vehicle for this many seconds across a specific driving pattern, we have observed that from the point of 0, which is mentioned here, we have a bandwidth of requirement for somewhere up to here, where you see largely the motor is operating within. And also at a slightly higher point, the motor also operates within this torque region. And then in some cases, it is operating within this bandwidth, and at very few requirements, it is also operating certain requirements at above certain requirements. So the majorly, I would say, 40% of the time, the motor operates within this torque bandwidth, and possibly here and I would say, other 30%. That sums up about 70. So and not about like another 20% here in this region, and maybe about like 10%. Now these numbers could be slightly different, and just I'm just giving a rough example. So what exactly happening here is the motor torque is continuously varying, and also the motor speed is continuously varying. So this is a typical requirements for an automotive application, because if you want to start your vehicle, so you need a large amount of torque to move the vehicle from static condition to velocity 0 to progress the velocity. All right. So the same way, if you have overtaking scenario, right? If you have uphill condition, so let's just draw some scenarios here. So if you have stop and start, so the torque requirement is really high, correct? So then if you have a scenario where you have to overtake someone, so then the torque requirements are quite high, because you press an accelerator pedal that you need to achieve that quicker speed in a short span. And then you can have uphill condition, right? Maybe if you take the vehicle in scenarios where there is an uphill condition on a hilly regions, so you have the requirement of a higher torque, or any of similar scenarios will demand for the higher torque. But it is not always that vehicle will be starting and stopping, right? So if you consider a city traffic scenario, so where you will be undergoing a lot of stops and starts, because you have a lot of traffic, you have a lot of signals, and you have a lot of people coming in front of you, crossing the roads and stuff like that. So it means that the vehicle is stopping and starting and stopping and starting. That means the transit torque requirements are really, really a lot. And then if you want to overtake somebody, for an example, highway scenario, right? So you try to overtake someone, that not only in highway, in normal road conditions too, you will have to accelerate the vehicle quicker. Or like right in similar scenarios, if you're trying to cruise on the highway, right? So the torque requirements are different. Like this, the torque requirement by the for the EV application is quite varying in nature. So that means the motor should be capable to deliver that all the torque at all every defined requirements. And also the other requirement is that the motor is efficient and highly efficient in certain points of operation. For the tractor requirements, the motor has to be efficient at all these bandwidths that you can derive the best out of the motor, right? So that is the typical given scenario for a traction requirements. So the one is, it demands the motor demands the variation. The motor should be capable of delivering the wide bandwidth of a torque, and also it should be efficient as much as possible in all of these torque bandwidths. Then also you will subject the motor into a lot of vibrations, right? Because you are driving the vehicle on the road, so there are a lot of potholes, there are a lot of scenarios of humps and things like that. So are the road unevenness. So you're subjecting the motor to undergo a lot of vibration, such as NVH studies would be very, very important. It is not something similar in industrial drive applications. Or if you take the temperature exposure, the motor would be exposed to a dynamic temperature variations, because you're driving the vehicle in, let's say, Bangalore, you're driving the vehicle in Chennai, you're driving the vehicle in Himalayas, or anywhere. If you take the vehicle across, the temperature it is exposed to is also completely dynamic in nature. So the motor should be capable of operating at wide bandwidth of temperature too, right? So like all these scenarios, the motor need to be very much functional and also capable and efficient in operating at various driving scenarios. That's the typical requirement of the motor for tractive requirements. That's why you just can't take a motor and then just assemble that motor into the vehicle and ask it to give you good performance output. So the motor selection has a lot of procedure in place that you can select any specific motor. So just moving to the next part of the slide, which is about the options that is available to choose the motor. So if you see in real vehicle applications, you have seen the variety of motor for specific requirements. So you have seen a very common application such as a hub motor, where you're trying to package the motor within the wheel itself. That's the typical, very simplistic approach of selecting the motor. But the problem is you have a lot of limitations in terms of the wheel diameter and also the wheel weight, correct? So it's good if you have a hub motor. Hub motor is the one where the motor sits within the wheel itself. So it's completely fine to have a hub motor, but there are some limitations. The limitation is the diameter of the wheel. And also the limitation is in terms of the weight of the wheel. So these two becomes quite important parameters when you're trying to implement the motor in the EV application. So what exactly happening inside the wheel if the wheel diameter becomes larger? Then there are standard tire sizes also that are available in the market. So you just can't fit any uneven sized tire into the motor. And also the considering the weight of the vehicle, so weight of the tire or weight of the wheel altogether, including tire, motor, and the wheel. So that becomes dynamically imbalanced at vehicle dynamic requirements. Let's say you're going at 150 kilometers per hour and you hit a pothole or you hit a bump, then because there's a lot of mass in the moving object, it would definitely undergo a lot of imbalancing scenarios. So maybe the vehicle itself will vibrate, or vehicle will lose its path, or anything can happen if you have the wheel which is completely at a high speed and it is hitting a bump. So in that scenario, so you would face a lot of vehicle dynamic scenarios, where vehicle dynamic issue scenarios. So it's in limited stage. So you can't really use a very large sized motor in the hub motor configuration. So you can only go until, let's say, like 2-3 kilowatt of a size. And then if you want to go for a larger than that, then you have to go for a non-hub motor configuration. The advantage of using a hub motor configuration is the hub motors are quite easy to package within the wheel. So your complexity of a vehicle packaging is very, very simple. So with that way, you will save a lot of space. You don't have a transmission that gives you a more liberty in terms of reducing your costs and stuff like that. But on the other side, you would also have some challenges in terms of uh, providing a better performance if you have a hub motor configuration. So that's when you could opt for a non-hub motor configuration where the motor is not in the hub. So you would go for an unlimited number of an option when you have a non-hub motor configuration. That means the you can have a transmission that is in between the motor and the wheel. So by varying large amount of gear ratios, you can play between the motor sizing concepts and motor optimization concepts and stuff like that. So and also you could have a small sized motor where you can play with the transmission gear ratios and concepts of that. So a lot of companies would definitely like to go for a non-hub motor configuration if you want to go for a better performance or slightly larger sized motors. If you're going for a small applications like 750 watt applications or a 1.5 kilowatt applications, for a scooter sizes, so you can definitely try going for a hub motor configurations. So in EV, so we also have a transmission, and the requirement of transmission may not be very, very large. But yes, we do have transmission in EV application. They're quite simplistic in nature. They may not be very, very large in gear ratio sizes. They're quite minimal in their design altogether. If you see here, Ather has just a one single gear ratio between your motor and the wheel in place. And similarly, Audi has a transmission design where they have a very simplistic gear ratios. So this is a typical configuration. So how do you choose a hub motor? How do you choose a non-hub motor? If the size of the motor, it means if the kilowatt of the motor is quite larger than a specific value, somewhere above 1.52 kilowatt, the motor mass becomes slightly larger. It becomes quite difficult to package that motor in the wheel, and then also you'd go into a lot of imbalancing the vehicle dynamic scenarios. So at that time, you would have to go for a non-hub motor configurations. So the point of operating points. So if you're selecting a motor, there are two ways how OEM will go about designing or selecting a motor. So if when you have a requirement, you may not have an exact available motor in the market. All right. So it's just like maybe if you're going to a shop, so you may ask for a specific object that may not be available. Maybe just like you're going to a carpenter shop and then you're asking him exact vehicle, an exact replica of a specific design. He may not be having it. but you either possibly you could just choose one he has, or you'd ask him to manufacture one that you want it as to be. So, but it's very expensive when you have to develop your own motors and for your own specific applications, right? So, because there's a lot of engineering activity, you need a lot of engineers from electromagnetics, motor design, cooling system design, and manufacturing. A lot of these aspects of motor design are required if you have to develop the motors in-house, right? So it's a very cost intensive activity. So keeping that as a scenario, if you cannot go for in-house manufacturing, you have to go for procuring the motor from some specific vendors available in the market. So if you are going for in-house development, so you would definitely have a better flexibility of designing the motor for a very optimized sizing. But if you have to go for a motor selection from the market, that okay, you have like 5 to 6 vendors, and they have designed specific motors for EV application, and now you want to just go and shop around with those vendors and try to choose them. So you have to do a lot of studies that what should be the size of the motor in terms of your kilowatt, and what should be the value of torque that you require, maybe in terms of the nominal, maybe in terms of the peak. What is the RPM of the motor that will be operated under, and what is the operating points of the motor? Maybe if you see here that the motor operates at various operating points, when you drive the car around, so it just the motor is operating in any of these operating points across the whole bandwidth, right? So when you see these operating points of the motor, so you want the motor to be operating at highly efficient points. If you see in this scenario, right, so if you see the 97 number here, so this is a point of the motor where it is trying to operate highly efficient in compared to the other points. Then you have a 96% efficiency bandwidth. Then you have a 95% efficiency bandwidth. You have about 94, then 93, 92, and efficiency started to drop down. So when you operate the motor, the RPM and the torque of the motor should be, if you want to operate your motor at a highly efficient region, right? So the motor operation should be above 5,000 RPM and below 8,500 RPM. And the torque should be above 100 Newton meter for this, and should be within this bandwidth, somewhere about 85 to 130 Newton meter torque. This is a portion where the motor is highly efficient. It's impossible that you operate the motor always at those operating points. Then you have to go for another option of operating points. So at this region, you can go for something like this, right? So in this region of operation. So where again, if you cannot achieve that portion of it, you can go for this portion of the operating point. So the idea is you need to evaluate where does the motor operate when it is running in the realistic scenarios. So what is running in realistic scenarios? The running in realistic scenario is you have various driving scenarios, like you're driving on a highway, you're driving on city, you're driving in a highly congested traffic, you're driving on a slightly congested traffic, you're driving on a highway which is like an autobahn where the high speeds are really, really larger, or you're driving in highways where the speed is about 80 kilometers to 90 kilometers per hour. So various these scenarios have been there in realistic condition. Or when you drive a vehicle, you may drive it very aggressively. When your parents drive a vehicle, they may drive it slightly slower. Or if a person who is a very well experienced driver, he may abuse the vehicle to the maximum of it. So it means that the motor RPM and torque has been drastically varying across all these bandwidths, right? So you want to know when you run the vehicle across all these life cycle scenarios, where does the motor operate at a highest at a very specific points. That's the scope of interest, to study the motor operating points, and then the more data you have about operating points and the subject to temperature requirements and all these studies, then you can actually optimize the motor design and everything as you want it to be highly optimal in size. So, but when you go for a selection in the market, so what you have as an option is you can try to choose a motor where it comes very closer to your requirements, right? That's what you could definitely try doing it. So or else it will be quite expensive to develop your own motor. So you would try, you have like option A, option B, option C, and option D. You would take care of this whole requirement sheets and then try to match. Also, definitely the cost is the most important parameter sometimes. So efficiency is also a parameter. Everything is like reliability and matching to the operating points, IP requirements of the motor. A lot of other parameters that will come into a picture when we choose a motor for an attractive application. So all of that is done in a place when the OEM select a motor. So a lot of engineers involved in performing simulations and stuff like that, so they could arrive to a very optimal requirement sheet, and then you can move on for the procurement as a part of it. So coming to the part of a motor, so also it is very important to think about motor cooling, right? So because definitely you have efficiency losses in the motor, and typically that efficiency get converted. The loss in efficiency get converted into a temperature, right? So you could tend to heat the motor, and if you have exposure to the motors, so the motor efficiency of the motor depends upon RPM of the motor. It depends upon the torque of the motor. It also depends upon the temperature of the motor. So if the temperature of the motor goes higher, then the efficiency of the motor drops down. So if you do not have a optimal cooling system, right, the motor cooling system, then you would impact the efficiency of the motor. And it means if you're impacting the efficiency of the motor, it means you're drawing more current from the motor controller, then you're drawing more current from the battery, so you get a less mileage. That's the end outcome of the if you do not have a proper motor cooling. So you could go for a air-based cooling, or a simple mechanism such as fans and stuff like that. But if you have very high increase in temperatures in a short time, so your air cooling system cannot perform efficient cooling, so you would have to go for a liquid cooling approaches in scenarios. So you may have to also understand how really the cooling can be done, because you need a refrigeration system that can take care of cooling the coolants. There's a lot of in-depth studies that anyone can take care of when designing motor cooling as an also option, but it's also quite important. So then once you have done enough activities of designing and selecting a motor, you also have to test the motor, because in realistic scenarios, anything can happen for the motor. So you have to subject the motor to a quite enormous bandwidth of operations and duty cycles and load conditions and abusing scenarios, so that you can study the motor temperature, you can study the motor behavior, motor performance, and maybe there is a vibration if it is at any specific values of the torque. A lot of these parameters can be observed when you do a motor testing. So a lot of companies does take care of definitely they have to take care of a motor testing before choosing any motor for any applications. So quite famous motor technologies or configurations are people trying to use are PMSM. That's the very largely used tech for EV applications today, because of advanced controls of density of a output that you can get from the sized motor. And also there is a axial flux configuration. Recently, if you have heard about Yasa Motors, which is a quite famous company in axial flux motors, they have been acquired by Mercedes-Benz. So they have been doing fantastic in terms of the optimization in size and weight of the motors. So that's I bet possibly that would be a technology would be adopted highly in electric cars or electric planes and stuff like that. So PMSM is currently the leading contender in the market, and the axial flux, and then the BLDC, and you can also see something on the induction motor. Like Tesla was using induction motors before, and now they're moving to the PMS and motor configurations, and also in the SRM motors and things like that, because there's a dependency of a magnet in these scenarios, but there is no dependency of the magnets here. So some OEMs and manufacturers would definitely try looking out for the other alternatives, because the materials like magnets are rare earth materials, so you may have to also be having concern about those components. So yeah, so you would definitely go for an induction motor or other SRM switch reluctance motors and stuff like that. That's about a very brief overview on motors. And jumping to the areas of motor controls, so it is exactly similar to what I can call it as a battery management system. But here you take care of a lot of power electronics coming in place, because it's not just only the controls. You also have to take care of converting DC to AC, and and then regulating that outputs, and then also putting that to the required value to the motor, right? Like how you have in charger. So as we discussed yesterday, so you have a AC, you need to convert to DC, then you need to regulate the DC and give an output to the battery. So similar way here also, because the battery is DC, right? Battery is DC, but the motors we are trying to use in all the EV applications, as I can call it, as are AC motors, right? So you're supplying DC from the battery pack. You have a motor controller which you can input. You convert the DC then to the AC, and then you also take care of regulating that exact amount of the current that should flow into the motor. By that way, you will control the torque of the motor and an RPM of the motor. So that's why you have a lot of power electronics that is sitting in the motor controls. So which is receiving the DC, converting that into an AC, and then supplying to the motor. So then you have the embedded electronics, right? So which is state-of-art controllers, maybe FPGAs and things like that. So they take care of all the switching requirements or all the control requirements of the motor, because you have algorithms like speed and torque control, field orientation control, field weakening control, and direct torque control. Like there are various type of control strategies that are available, algorithms that are available. They involve in controlling the motor. Again, there is something like sensored motor and a sensorless configuration. So again, there are a lot of approaches through which you get an input of the reference value, and then you control the motor output. So all these algorithms, like how we have in BMS, like SOC estimation, SOH estimation, SOP estimation, the same way here to ideally deliver that exact amount of torque, exact amount of speed of the motor, you have various different type of control algorithms. So all these control algorithms have to be put inside this controller, and that has to be also designed in a very proper way. So you could also see, like in algorithms where I was mentioning. So for example, if you're taking of a vehicle, like you have various different modes. Like this is an image from Aether. So you have a sports mode, you have a ride mode, then you have an eco mode, right? So what they define as eco mode would give you a highest range, because it limits the maximum torque. If you draw a line around here, right? So the torque is limited, and in the ride mode, the torque is slightly higher, but in the sports mode, the torque is higher, right? So it means the torque is directly proportional to I. It means the current you draw from the battery. If you're drawing more torque, then you're drawing more current. If you're drawing more current, then you're drawing more energy from the battery, right? So that means the more energy has been consumed, so you would get a lesser range from the motor, from the battery, or from the vehicle as in place. So all these control modes, like if you just, all you do as a customer is just press a one button, or you touch the screen option, right? That I want to go for a eco mode, I want to go for a sports mode. But in a vehicle condition, the motor control takes care of, all this sitting is inside this controls, right? So there are different algorithms and limitations that they have set in the motor, that if you have a eco mode, then you don't want the motor to draw more than a specific current value. So all this kind of an state-of-art algorithms are sitting inside the motor controls. But also if you take examples like, the hill assist control. So if you are on a, if you have parked your car on a, for example, slightly inclined road, right? So you tend to come back when you try to lift off the brake in the car or a truck or something like that. So then you tend to hit the person or a vehicle which is behind of you. So what control algorithm that you can design is like you can have an algorithm that if the vehicle speed is this, that you don't want the vehicle to move back if it is in a drive condition. So you have some of these algorithms that are sitting inside the motor controller. The motor controller assists the driver not to let the vehicle to go back. So that means it's like very comfort for the customer, because if you have driven the cars around on amazing roads, you have traffic lights on a uphill condition. In some of the places, you're on the traffic light, but you're on an uphill condition. You're parked your vehicle, and there's a green signal, and everybody is honking back of you. You may let the brake to go off, the vehicle start to move backside, right? Even when I was learning the vehicle in the very beginning days, it was a very scary scenario. So that is something you need to be concerned about, and these are all the control algorithms that you can actually implement in the motor controls, and let it take care of all that scenario where it can help you to assist the driver. So at Decibels, we have been opening up the courses on designing of the embedded hardware. So where you can actually use a design softwares like KiCad and design these motor controllers, and also funfully you can manufacture them, and also maybe you should be able to also test them and run them. So we have been teaching learners on how you can actually design a motor control for the censored application, for the sensorless application, in as it is a requirement in the industry. So it is a quite funful activity. You can definitely engage at Decibels Lab if you would like to learn. So all we're trying to do is trying to make you better equipped for the scenarios tomorrow. So before a learner graduates out of the college, or possibly if somebody's already graduated and they want to upskill themselves to meet the industry requirements, so we are trying to create courses and trying to create content, and there you can gain a complete practical learning experience and exposure. So if you're interested, you can definitely get in connected with us in the tomorrows that we will share you the feedback form. If you're interested, definitely you can get in touch with us. We'll be very happy to teach you those syllabus and content, and that will be making you as a subject matter experts in various different areas. So at the last slide here, I'm sorry, this is continuation of the chargers, so there should be the motor controller. So you have similar requirements as such as the chargers. So you would definitely have exposure to power electronics. You should have exposure to hardware architectures, functional safety, and a lot of things in EMI compliances. It's standard for automotive requirements. There is no different stuff like that. So if you go down to the other side on the software side, definitely you need to have the exact similar requirement. What you could design a BMS, or what you could design a charger. The similar way you can also use the same skill sets in designing motor controls. But you would definitely need to have some subject matter expertise to work on motors, because you need to know the application end for EV, how it behaves, what dynamics are there in EV, what kind of scenarios that would realistically come down in applications for EV. So for that, you need to have some exposure to motors and application as EV and its controls as a part of it. So, but rest is all typically in a similar overview in place. So that's pretty much from my side for the today's session to cover up on motors and motor controls. And quite an overview. I totally agree. It is not possible that we can teach you the in-depth of motor controls, where you can go for a Clark and the park transformations, where you can go for any other type of details that we can teach you. But we have courses that definitely can help you in engaging and learning at Decibels Lab. So if the floor is open for questions, if you have any questions, please do drop the questions across the chat box. Or if you just let me run through what we have on our platform. So if anybody is interested, definitely you can explore some of these programs that can definitely help you to gain a definite learning exposure on any of these areas of EV. So by the way, in the meantime, if you have any questions, so certainly you can ask ahead. So all you have to do is just go to our website, lms.decibelslab.com. So we have some master courses where we are promising 100% placement. We are the only organization where we write a contract with a student that we tell, if you take up this program, that is guaranteed to have a placement. And if you're not getting a placement, we also provide a stipend and pay until you get an employment. So I think everybody who have interest on EVs in continuation today, you can start with either on powertrain sizing, and you can start on lithium algorithms, or you can also work on power electronic simulations and also on the motor control algorithms. Those are all the courses which are highly practical in nature. You can get to build the models in softwares like MATLAB, and where you can actually simulate them. You can understand the logics of motor controls, you can logics of the BMS algorithms, SOC estimation algorithms, and the component sizing for motors, component sizing for battery, everything in depth that how industry exactly does. So you can start to specialize yourself. If you're a guy from mechanical engineering domain, you can look for either on powertrain sizing, or you can look for battery algorithms. If you're from electronics, you can take care of lithium cell modeling and algorithms, or you can take care of motor controls. Or if you're from an electrical guy, you can definitely take care of component sizing again, and also the motor controls. So amazing program. So we're also going to issue some discount coupons for the participants who are taking part in these courses, which is basically a 5-day foundation program. So that will come across to you. One of my team member would definitely communicate an email, so where you can take some better pricing for this program. So you can also engage and learn in through this contents. So great, that's pretty much from my side for the session today. If you still have any questions from today's discussions we have, so kindly share across your questions in the chat box. I should be glad to address them with my knowledge. Great. So I believe the session was interesting. I believe the session was informative. I believe you were able to gain some exposure to the motors and the areas of controls. I believe you enjoyed all the 4-day sessions and 4 sessions altogether. And tomorrow the session would be handled by Mr. Krishna, so he's a simulation engineer. Tomorrow will be a practical classes. Please do have your laptops, and also please do install the Excel software, Microsoft Excel, because we will require that software for performing motor sizing and battery sizing in tomorrow's session. So fantastic. So if there is no questions from anybody, so thank you very much for taking part in this session. Thanks a lot for showing the interest to learn and staying back on holidays to engage in the learning activities. Thank you very much, everyone, again. And we look forward to see you tomorrow in the practical sessions. Email will be sent across to everyone to join the meeting. And all of these sessions will be uploaded on our LMS so that you can just go and revise. And also the sessions are available on our YouTube channel, so where you can also go and jump in for the learning. So I believe it was interesting and it was enjoying for all of you. Thank you very much again. Good night, everyone. Take care. Bye-bye. Ankush, yes, there will be um, sessions that we are leaving on our YouTube channel, so you can surely watch them anytime whenever you have time on our YouTube channel. Yeah, videos are always available. Although LMS do have a limited duration, so I think it'll expire by 20th of this month possibly. But yeah, you can generate your certificates before that. And but the videos are still available on our LMS too, and also on our YouTube channel, so you can definitely take part in them. So yeah, this is a live stream where we're interacting right now. So yeah, so you could also have this recording in a YouTube channel. So, well, when is the next session tomorrow? The next session tomorrow is at same time, 5 p.m. IST. So I think, yeah, it will be on YouTube. So we would definitely discuss. We request you to, follow on the emails that we're sending. We're sending an emails to everyone at 4:45 to join the session. So yeah, so you could get an email tomorrow too. So I believe you have been enrolled on our courses, so to receive the emails. And yeah, definitely we will upload similar sessions on our YouTube channel too in the live. Great. So I think that's pretty much for today. If you have any other questions, we should be happy to